I'm Shreyansh.
I'm Tim.
I'm Charudhi.
And I'm Rob, and we're Reaction Faction, and we're here to bring you our project, Raising Cain. First, I'd like to give you a little overview of what we're going to be talking about today. First, we have our process description, then we have a literature review, base case selection, plant location, process economics, an economic evaluation, and then the key issues that we kind of had during our process. So, first, I'd like to talk about a project description of what we were actually trying to do. So as you know, we were trying to take sugarcane and make jet fuel out of it and kind of look at the ins, outs, ups, and downs of what this process entails and is it economically feasible? Should we endorse this or tell somebody that yes, you should invest in making our plant? What came along with this was that we found a very sustainable process and we had high hopes for the beginning of the project with regards of economic feasibility and that it could actually happen. So I would like to first let Shreyansh talk about our base case selection.
So at first, I'm going to talk about the base case selection. A number of alternatives were considered before settling for the base case. As per currently, the fossil fuel-based petroleum refining process dominates the aviation fuel production industry. As of 27, an average refinery produces about 10,000 barrels per day, and our biorefinery was sized with the objective to compete with it. The current design generates about 4,300 barrels per day, which is approximately 40% of the petroleum refining production. The rate of production requires milling of 3,900 tons of sugarcane per hour, which is just over 3 times the mass of sugarcane milled in ethanol producing plants. Talking about our literature review, the design team determined production of hydrogen and C12 jet fuel via pathway 1B and 2 respectively, as we can see in the slide. Next, the reason of choosing this pathway was, first, it maximizes the jet fuel production and it helps us compete with the refinery. Second, it reduces greenhouse emission gases. Third, it functions as a nearly standalone process producing hydrogen, heat and electricity, which are used to supply throughout the process. Furthermore, the sale of hydrogen could increase the plant's economic lucrativity, and also the generated excess heat and electricity could be sold. A number of additional factors were chosen before selecting the base case. A major one was a simple process design, which helps to reduce the capital and operating costs significantly. Now, talking about the plant location, both the raw material and final product are bulky, hence logistics would play a big role in economic feasibility and highlights the importance of selecting a correct plant location. The major criterion for plant location were availability of raw material nearby and proximity to the customers. As per a survey in 2010, world jet fuel consumption totaled to be 5,200,000 barrels per day, with United States consuming about 28% of the world's jet fuel, which is about 1,400,000 barrels per day. The United States is a chief consumer, and our team is going to be catering, and our plant is going to be catering mainly to United States. As such, we wanted our plant to be located closer to United States. And talking about some top countries for producing sugarcane, as we can see in this table, the first is Brazil, followed by India, China, Thailand, Pakistan, and Mexico in descending orders. Sugarcane is a bulky raw material with costly logistics, hence it's favorable to situate our biorefinery closer to sugarcane supply source. Constructing a plant in the United States would result in logistic savings, reduced government regulations, and potential for government subsidization. Unfortunately, the United States is responsible for only 2% of the world's sugarcane production, as we can see in this table. Furthermore, the valuation of sugarcane is about 40% higher in the United States than the rest of the world, as shown in the table on the left. Hence, considering the United States wasn't an option, and considering the forementioned constraint, Mexico provides to be a suitable location for our plant due to the proximity to United States and having a reasonable sugarcane production. Also, United States government has good business relationship with Mexico, reducing potential for downstream difficulties in production, exportation and sales. It is assumed that our plant would be constructed on a pre-existing ethanol production site in northern Mexico close to sugarcane farm. Tim will now talk about our process description.
Okay, our chief process input, sugarcane, up here, is directed to a cane mill, which results in our outputs bagasse and sucrose. The bagasse is a stalk-like cellulosic material which can be combusted, burned to produce heat and electricity necessary to supply our plant. The sucrose is going to be the input that allows us to produce our jet fuel, our chief product output. The sucrose is fed via one of two pathways, either the blue pathway shown here, which ultimately results in the production of hydrogen, or in the red pathway shown here, which ultimately results in the production of our desired product, jet fuel. The blue pathway, a fraction of the sucrose is directed down the blue pathway to our first fermentation reactor A, which results in production of ethanol. This fermentation reactor A operates as a batch stir tank reactor and operates and requires 48 hours. The product ethanol is directed to a holding tank. After the ethanol reaches the holding tank, the process operates continuously thereafter, with the product ethanol being directed to a fixed bed steam reformer reactor, which produces hydrogen, which is purified and stored in our hydrogen storage tank for use in downstream processes. The remainder of the sucrose is directed down pathway B, our red pathway. By iterative method, we determined that 92% of our sucrose would be required to be, or 8% would be required for our blue pathway. Our red pathway would require 92%. So the 92% of the sucrose is directed towards fermentation reactor B, which results in formation of 2,3-butane-diol. And that reactor operates as a batch stir tank reactor with a 42-hour reaction time. After the reaction is completed, the 2,3-butane-diol is directed to a 2,3-butane-diol holding tank, BDO holding tank, and from there the BDO is directed to one of two BDO dehydration reactors. The BDO dehydration reactors receives an input from the BDO as well as a sulfuric acid input necessary to conduct the reaction. Each reactor requires 1 hour of reaction time. We have two reactors on service, so the one reactor can be filled and drained while the other is while the reaction is taking place within the other. Ultimately, the product from the BDO dehydration reactor, methyl ethyl ketone, is directed to the is directed to a sulfuric acid treatment unit. In this unit, we remove the corrosive sulfuric acid from the product stream. This is important to minimize the corrosion of our plant materials, piping, things of that nature, and just to promote overall plant safety and maintain integrity of our process. After the sulfuric acid is removed via reaction with calcium carbonate, the methyl ethyl ketone stream is sent to a methyl ethyl ketone holding tank here, and then thereby fed to a methyl ethyl ketone trimerization reactor, which operates as a batch stir tank reactor with a 6-hour reaction time. Upon completion of the reaction, the product's C12 ketone is directed to a moisture separator, which effectively removes the water from the stream before being directed to a holding tank, the C12 ketone holding tank. After the C12 ketone reaches the holding tank, it's then fed to the C12 ketone hydrodeoxygenation reactor, where the C12 ketone is converted to C12 jet fuel by removing the oxygen component. The effluent of the C12 ketone HDO reactor is sent to moisture separator B, which further removes moisture from the stream before discharging to an unpurified C12 jet fuel holding tank. Beyond the unpurified C12 jet fuel holding tank, the process operates continuously, being fed through the moisture separator C, the BDO separator, and then ultimately our C12 jet fuel distillation train, which removes our C12 jet fuel through the top, with our heavy impurities being removed from the bottom. And now Charudhi will discuss some of our process economics. Rob will discuss our process economics.
All right, so I'm just going to get us started with some process economics. We'll have Charudhi come on and help us out some more as soon as we get us started. So the first relevant thing we decided to look at when it comes to economics is how much is this actually going to be worth? How much can we actually get out of this process? And as you can see, jet fuel is $2 a gallon, roundabout. We used exact numbers in our calculations, but just for now we'll go with $2. And that's based off of crude oil prices. And we we found through research that it would be 1.3 times higher for jet fuel prices. And our sugar cane comes out to $42.49 per ton. And just analyzing all of this, we were able to get a first rough estimate telling us that this process may not be economically feasible. We tried to think of other ways to offset these costs, as you can see here, with sale of ethanol that we make from process A, as Tim had discussed, and we also had the sale of surplus electricity as well as carbon credits, which were not too highly valuable, but still offered some offsetting costs. I will hand it off to Charudhi to talk more about economics.
I'm going to further on talking about the economics that Rob started us on. So the three main categories, as you can see, to evaluate the costs was first raw materials, which included sugarcane, catalysts that Tim spoke about, calcium carbonate, sulfuric acid. The second main category and the most major contributor to the economics was utilities, which included things like electricity, refrigeration, low pressure steam, high pressure steams. The third category was fixed costs, which was repair and maintenance, insurance, and labor. We made a lot of assumptions, especially for the fixed costs. As you can see in the table, there was things like property tax, insurance. For example, for the property tax, we said it was 2.5%. We assumed that there were about 32 people working on our plan, and we assumed different operating capacities throughout our cash flow model, such as 25%, 50%, as well as 100%. Also, while we did calculate our economic evaluations, we did not include any byproducts because they were left unseparated and therefore did not yield any profits. Another major thing to note about our economic evaluation was that it was based off of how much jet fuel it will have to be sold for to obtain the desired annual rate of return, which is 15% for our project. After we conducted all calculations, we got a total price for our plant to be 142 cents per pound, as opposed to the actual price that it's currently being sold for, which is 20 cents per pound. Obviously, you can see there's a major difference, which yields our major concern, which is economic feasibility of our plant, because it makes it really difficult to sell something at such a high price when the current price is so low. From here on, I'll talk about the sensitivity analysis, from which the first category is price. Obviously, as you can see from the bar chart, there was a steep increase in the price of fuel at one point, which makes us optimistic about the fact that our plant might be feasible. But at the same time, we need to keep in mind that there was never a point where the increase was so much as to be able to make the plant that we have actually feasible. The second major thing is the sucrose yield. Currently, the sucrose is 14% of our weight when we mill sugarcane. Even if we do assume genetic modification and the fact that we might have more yield, calculations suggest that that as well would not yield profits for our project. The third thing, is the utility cost, for example, for the cooling water, which is 40% of our operating cost, which is a really huge amount. We calculated that reducing that cost would make the economics a little more favorable. The last category for the sensitivity analysis is our technological advancement. Firstly, we know that our project is batch run. If we find a way to make this a continuously run project, it might yield more profits, or at least make the economics more favorable. Other advancements, like advancements in condensation reactions, trimerization reactions, might also make this project a little more favorable. A few recommendations that we thought about was, given the economic feasibility of this project, we would not suggest this project to be carried out. But if it is needed, we'd suggest that this project has a potential to reduce greenhouse gas emissions, and therefore it could provide and promote economic sustainability. Some key issues that we encountered while we worked through our project was, of course, foremost, competition of sucrose with other industries such as the food industries. And as we just spoke about it, the economic viability, as well as the current trends in jet fuel prices that are not encouraging at all. In terms of the process and equipment, one of the major concerns is that it is in fact a batch reactor, which has less revenue capabilities as opposed to a continuous reactor. Secondly, we noticed that the sizing of the equipment could in fact steepen initial capital costs. I'm going to leave it to Rob to conclude.
So, just concluding what we've talked about and kind of going over what you learned for today, was that this process was a really, really in-depth, very neat idea, I would call it. We were taking sugarcane and we were trying to make jet fuel. However, when it came down to it, due to the economics and due to just the sheer size of how we had to run this plant in order to try and be competitive, it's just not feasible, and there's just no recommendation towards pursuing this idea at all at this time. We'd like to thank you for your time, and if you guys had any questions. And thank you, Dave and Don, for a great class and being a great mentor.